The purpose of this video is to understand the interpolation operation in time domain, which is used for sampling rate conversion. So in a previous video, we saw that if you want to get an interpolated signal, which is as if you are changing the sampling rate by a factor of L, then the way you should do that is you take your input sequence x of n, you upsample it by a factor of L to get the expanded sequence xen, you pass it through an interpolation filter, which in an ideal setting should have this form. So the interpolation filter has a gain of L with a cutoff frequency of pi over L. It's a low pass filter, and it's 0 outside that range, and we get xin. So in the previous video, we saw that the Fourier transform of this xin, which is xi of e to the j omega, we saw that that is simply xi of e to the j omega equals to the Fourier transform of course, your expanded sequence xe of e to the j omega times hi of e to the j omega. Okay. This is the time. This is the frequency domain operation. The question is, what is the time domain operation? Well, the time domain operation, of course, we take the inverse Fourier transform. So we get xin. That is simply going to be the expanded sequence xen convolved with the interpolation filter, the impulse response of that filter. Now that, if you remember the last video, we had explained that the expanded sequence can be written as k from minus infinity to infinity del x of k, the original sequence, times delta of k n minus kl. So I'm going to use that relationship here. So I have k from minus infinity to infinity, x of k, delta of n minus kl, and then I am convolving that with hin. Now, since convolution is a linear operation, all of this actually gets inside the summation. This xk is not a function of n. This acts as a scalar, so I get k from minus infinity to infinity, x of k, delta of n minus kl convolved with hin. Now, let's stare at this and remind ourselves of the convolution property of the delta function. So remember that if I have a delta function shifted to n naught and I convolve with another function f of n, then the only effect of that is that the whole function gets shifted to n naught. So if I apply that property, what I get is k from minus infinity to infinity, x of k, hi of n minus kl. Okay. So this is what is happening in the time domain. xin is given by this expression. Okay. Now, what exactly is this expression doing? Well, let's assume that your xn was originally this kind of a sequence, and we upsampled it by a factor of 3. So then what we get is I have this, then I get 2 zeros, then I have negative, then I get 2 zeros, I have positive, then I get 2 zeros. This is my expanded sequence, xe of n. Okay. And what this expression is saying is that you are going to basically, whatever is the impulse response of your interpolation filter. In this case, right now, let's not get into the discussion of that. The interpolation filter is going to have a sinc expression, but what we see is that the interpolation filter is saying take the first value and multiply it with your interpolation filter and place it at this point. Then the next value, you get your interpolation filter hi of n minus l. You shift your interpolation filter at this location, multiply it with this negative number. Similarly, take your interpolation filter, shift it to 2l location, multiply it with this number, and then you add all of these things up. Now when you add, so interpolation filter is of course going to have a long length. So what is going to happen is that when you add these three different shifted versions of your interpolation filter, these zeros will start filling up with other values. So effectively, you are filling in these zeros with values based upon what values you had at your first value, your second value, your third value. And because of that, you are interpolating the values that you did not know. Now, when is this interpolation perfect? Of course, we already derived that the interpolation is perfect when my low-pass filter, when I use a low-pass filter, an ideal low-pass filter. So let's look at what is this interpolation doing in the ideal case. So what about the ideal case? Okay, in the ideal case, remember that a low-pass filter has the impulse response given by sine omega cn. So omega c is pi over L n over pi n. And in this problem, we have a gain of L. So instead of 1, we have a gain of L. So I can actually now write that as a sinc pi L over n over pi L over n. So this is my ideal interpolation filter, or what we should call a discrete sinc. In particular, what we know is if you use L'Hopital's rule that the sinc at 0 takes the value 1, and at every multiple of L, you can verify that this sinc will take 0 for all n that are multiples of L. If you have a multiple of L here, you are going to get sine pi, or sine pi multiple of sine of multiple of pi, sine of multiple of pi. Now sine on any multiple of pi is 0, so the numerator is going to be 0, the denominator won't be 0. So hin will be 0 at those locations. So what are you getting then is that in the ideal world, when we low pass filter, we are doing sinc interpolation in the discrete world. In the discrete world, at this location we have a sinc. That sinc is 1. So here we'll get exactly this value, because all the other sincs that are adding up here will pass through 0 at this point. But at these initial 0 values, these things will add up to give you something non-zero. Okay? So in the time domain world, interpolation is effectively just doing sinc interpolation, which is that once you expand the sequence to a longer length, it just uses a sinc and adds up all those different sincs, the shifted versions of the sincs, to give you the values in between. So in that case, my xin is simply k from minus infinity to infinity, x of k sine of pi over L n minus kl over pi over L n minus kl. Okay. Now, a couple of comments about real-world interpolation. So when you do actually interpolation in MATLAB or any other computational tool, you cannot use sync interpolations because sync has infinite support. So sync goes from -infinity to infinity, and you don't really do interpolation with a sync. So in the real world, the interpolation filters that you use are typically linear, which is perhaps too simple, or cubic interpolation systems. In particular, upsampling is very common when you do images, which are 2D signals, and you will often hear the word of bicubic interpolation in the cases of images, which is nothing but basically doing upsampling, and then instead of using a sync filter, an ideal low-pass filter, you use a cubic filter, which comes close to a low-pass filter, but it doesn't have a brick wall effect. The last point to mention here is that in the case of decimation, remember that even if you do not have the low-pass filter in downsampling is used to avoid aliasing. If you don't have a low-pass filter, you can still live without it. In the case of upsampling, however, if you do not have a low-pass filter, you are not going to get real interpolation. You are not going to get a signal that looks like your original signal sampled at a different frequency.